Okay, all right, so as a show of hands, how many people here are taking programming two? I'm just trying to get a general idea of where people are. Are you taking programming two in the front?
Oh, I have.
Okay, cool. How many of you taking comp org? Great, this would be a piece of cake. I can like skip through most of the front of it. So this is binary exploitation, which is kind of like a major subset of Pwn. And a lot of people who aren't familiar with either Rev or Pwn kind of get them mixed up. Generally, the main thing is the whole point of Rev challenge is to decode a binary, to reverse engineer it. With Pwn, there is a lot of that. Sometimes you get a binary file that you have to decode, but the point is to find an exploit and exploit it on the server that they host. So unlike Rev, where the flag is somewhere inside the binary, it's not in a Pwn binary. Your goal is to find an exploit you can use remotely, and they will have it on their remote version that you don't see. So we're just going to go over kind of basic program stack. You guys have already taken comp org, so you should know this pretty well. We have a base pointer, a stack pointer, and this is kind of what happens when we call functions. They'll move like this. That yellow is really hard to read. Good Lord. That's this function B. And then when we're done with the program or with the function, the stack will move up and the memory is effectively forgotten. And we move back up. Why is this important? Well, because a lot of what we do is mess with the stack, right? There's a lot of important things on the stack. If we look at this from a assembly level, how do you look familiar with assembly, like x86 assembly? Okay, that's pretty good. Basically, the push instruction there will push something onto the stack, so it'll move things down to store value. Move is just a copy, so that's all you're really going to need to know. Calls a function, and returns from a function. Basic language stuff. And if you look at like the main procedure, you see what happens at the start of a function is you'll push the base pointer, you'll save the old one, you'll override it with the current bottom of the stack, and then you'll move your stack down when you add stuff. So that's how you make your own stack. You'll do your calls, whatever, and then at the end, you'll move your stack pointer back to where the top was of your current function, and then you'll pop off the previous base pointer. So it'll look something like this, and the pointers will move in that order. And then when they're done, RSP will come up, RVP will come up as well. So right, RVP is the base pointer, RSP is the stack pointer. R just means it's 64-bit because modern computers are 64-bit. So if we actually look at this from an individual frame, right? So at the top, we have top addresses, like high addresses. At the bottom, we have lower ones because the stack kind of moves down. Does anybody want to tell me the first thing that's going to go in this when you call a function? Anybody at all? Literally anyone. I don't want Dean to do it because he knows the answer. There's 4 people in this room that I don't know. Come on, guys. When you hit call, all right, fine, I'll give you help with this one. If we have this function here, right, the first thing to go is RIP, which is the instruction pointer. So, right, you got to remember that a CPU kind of just runs instructions one by one. It doesn't know what a function is. So if we want to go back from where we called the function, we need to store where that was. So this is after that RIP is the address of after you call a function. Where to go once we return from whatever we're doing. Now, this one I really hope you'll know if you paid attention to the last slide. What comes after this one? Their RIP. You guys can't hide. There's like 5 people in the church. Come on. There's like 2 you can think of at a time. Nobody. Please. Elbow, something.
Like, add more space to the stack.
All right, but we have to store something first. All right, I'll give you this one too. RVP. This is the base pointer. So this is what we're doing is we're saving what the old stack was, the old stack frame, because we want to make a new one. And we want to make sure that we can return to that old one. Am I going too fast? Okay, cool. This now it gets easier. Look at that. You see the function there. It's got a char and then an int and a magic number. What comes after this base pointer in this stack function? Come on. Dean, you can answer now.
Valid?
Yes, there's a char. So we can fill 1 byte in this stack frame because char is 1 byte. That's where valid lives. They got a little block. So what comes after it? I swear to God.
It's the next variable.
Right, which is?
Magic number.
Great. Where does that go on the stack? Exactly. Which spot blocks?
Well, if you've only done, it's a byte line, like 8 bytes.
What do you think?
Like, does it go under or just right next?
What do you think?
I think it's the next line.
The next line?
Yeah.
Okay. It goes there. So ints are 4 bytes. That's a really good point. That's why it's here. I want to bring this up. Ints are 4 bytes. When you have a value instruction, when the CPU actually looks at that value, it is aligned to its size. So this can't go right next to the yellow one. It could go to the next line if it wanted to, but we want to be somewhat efficient. So we're gonna put it there, where it's on a 4-byte boundary. It's that middle one. After that, we're gonna put an input, which is 12 bytes. So this is a buffer. These are all individual bytes, so we can put them wherever we want. Anybody want to tell me what point this goes? Still long. Dean, you know? Yep. Because we can't split it up. It's got to be on a boundary. So there. So that's a basic stack frame. But if we move on from that, we actually talk about buffer overflows, which you've probably heard of because they're exploited all the freaking time. Basically, a buffer in memory is kind of just anything really. We like to think of it as like an array or a vector or whatever from whatever language, but really it's anything in memory. It could be a number, whatever. It could be whatever size here, there, whatever. So if we have a function like this, all it knows is the buffer starts there. It doesn't actually know how long it is. So we have this gets call. What that is going to do is it's going to pull standard input from the terminal. So it asks you to type something down. It's going to put in the buffer. We could, put in 16 bytes. We could put in 4 bytes, 4 characters, or we could just put in however much we want. And that's what a buffer overflow is. We're basically writing the memory that we shouldn't have. Yeah, so if we have this example exactly, we have an integer, and then 4 bytes, and we call gets on that buffer, right? Our intention is you can only write 4 bytes. What's actually going to happen is you can write however many you want. So we immediately print out what x should be. In a good situation, it's going to be 0. But if I type in 8 characters instead of 4, it's going to give us 41, 41, 41, which is the hexadecimal value for A in ASCII, which is, but that's kind of, what do we really do with that? Okay, so what? We can overwrite a value. How's that helpful? Well, as we talked about before with the stack frame, the top thing in a stack frame, technically before a stack frame, is the instruction pointer, where we're going to go after we leave a function. So what if we overwrite that thing and just change where we're going? So if we have this function, if we have this setup right now, we have a win function, which prints out the flag, whatever, who cares? And we have a main function, gets an unlimited amount of bytes. What it's going to do is it's going to check if we typed in password. And if we did, goes to the win function. Cool. And ideally, we don't know what password is. Well, if we can write as many bytes as we want, what if we just, instead of writing the answer, we just overwrite what's in RIP? So this is the stack right now. That yellow text, that white on yellow says buffer. I can't read it from here, but just leave me. But if I keep writing past buffer, I can get rid of RBP, completely destroy it, and put in the address of win at the top. And what happens is when the function tries to return, it's going to go to that function, right? And the problem is you can't exactly type the address of the function in your terminal. I mean, you could try. I go for it, man, whatever you want to do. But ideally, we'll use a tool, which in this case is called PwnTools. It's in Python, which I hate, but it works. If you want to install it, use either of those commands. If you're on Kali, Debian, whatever, use the second one. And what a PwnTools script does is it automates input, right? So if we start our Python script, all we do is we import it, and then we have this thing called an ELF. And ELF stands for execute and link format, I believe. It's the format of binaries on Linux, libraries, executables, whatever. So what we're saying is basically we want to load the binary called binary and put it into ELF, right? We're storing the binary. It's going to have information about it. What we can do is we can say elf.process. We can start a process. Let me send input, let me receive input, whatever. The cool thing about PwnTools is when this exploit is ready to go, I can just change elf.process to connect and then IP, and the exploit will work like it was working locally, except it's on the final version. So the first thing we're going to do in this case is we're going to just clear out all the output they gave us. So the first thing it said the first thing that they printed was what's the password. So I want to receive until we get that. So we just clear out the buffer. Then I want to send my payload, right? I want to send that exploit we're talking about. We want to overwrite the return or the instruction pointer. So we're going to make a payload. What the flat function does is it basically just lets you say at this point in the input, put this value. Otherwise, it just fills it with garbage. What we're saying is the buffer that is 16 bytes long is the only variable we have. And then there's 8 more bytes to get past the base pointer, the RBP that we talked about. And now we're at the instruction pointer, right? What it's going to do is just going to put in a bunch of A's until we get there. What we're going to put there is this kind of stupid looking function. T64 just means I want to write it like it's a 64-bit value. And then elf.symbols.win is get the address of the win function, right? The pwn tool will help us do that. Otherwise, you'd have to open up a disassembler, and yeah, it's kind of a pain. So now we can actually see what's happening. It's easy to read. And then what we can do is just send that payload. And if we do that, we can then read out that flag to give us, so ditch the first line and print out the result. And if we do this, when we run it, we'll get a bunch of debug info that we don't really care about, and then it'll print out that the flag is line, even though we never told it what the password was password, because we just completely skipped that part. So that's kind of the essence of doing a buffer overflows with in a stack like this. So we have a slightly more complicated function. All I've changed is I've added kind of that verified value. The point I'm trying to make by having this is that this is not a solution, right? Because if you look at this, you might think, okay, we don't set verified until we get the password. So if we jump to win and we're not verified, it'll just kick us out, right? Not really, because we're putting in an arbitrary address into the instruction pointer. So instead of just jumping to win, why don't we just jump right here and get the answer anyways? So, stuff like that. I'm trying to, with this whole presentation, is not really go into super details about how to do these, but more kind of give you the puzzle pieces. If you're interested in this, I would love to see you on the weekends, and we can do more stuff like this. But we have a bit of a problem, like that said, that basically you never have a function that's called win. That's really bad design, in my opinion. Maybe, Zuckerberg will disagree, but whatever, Elon, But so how do we actually call a function with values, right? Because when are we ever going to have a function that, again, just gives us the win? So if we want to do something like that, we're going to need to do something called return-oriented program, which we call ROP, because who wants to say that 3 times fast? And the idea is that we have a function like system that's supposed to have an end parentheses, but just pretend it's there. We're going to call system with bin sh. That's going to give us a shell. Usually that's kind of our goal, right? We want a shell that we can actually type things in, run arbitrary commands. So we want to get to this point where we can call this function. We know where system is. Let's just pretend we do. We'll talk about that later. But we've already talked about how to jump to some function. We can do that. The problem is, how do we jump to, how do we put this value into the function, right? How do we actually get that argument there? Because all we have is the stack. We can't just write code. And so, to do that, we need to think about how these are actually laid out. This is the calling convention for Linux 64 machines. And the only thing that's really important for you to understand here is the first argument is stored in the register RDI. Registers are little chips on the CPU. If you took Cloud Core, you should know that. But our goal is to set RDI. How do we do that with just the stack? There's not really like, it's not like we can just write a move instruction, it's the stack. So what we have to use are something called gadgets, right? And what the heck is a gadget? Well, it's a fancy word for this mess. And don't get scared, because literally the only one that's important for you is that one. This is a dump of a bunch of gadgets in a binary. With a tool we'll talk about later on, I'll give you the resources for that. But right there, what that first line is saying, at address 1799FF, there is the instruction pop RDI followed by ret, so followed by return. And why that's important to us is if we're doing a pop instruction, we're pulling from the stack, which we have control over. So if we're taking something from the stack and putting an RDI, we're effectively setting this register using only the stack, which is very handy. So when you look at this from kind of more of a stack frame view, and this is supposed to load a little faster, that yellow text is REP. If we're the first instruction of kind of like leaving one of the few, the second to last instruction of leaving a function is pop RBP. And after that is return. So what we're doing is we're returning into the address that has the instruction pop RDI ret. So if we do that, the stack pointer will move up. So now the next instruction that's going to be called, as you can see on the right, is pop RDI. And right now on the stack is a string bin sh. So what's going to happen is going to put bin sh into RDI. And then as part of the end of that gadget is another return. it's then gonna return into system. So effectively calling system bin sh using nothing but the stack, which is pretty cool in my opinion. And you can stack these as much as you need, sometimes 4 arguments.
Can we pause real quick? So
Yep.
like to emphasize, like this is the stack, RDP is a value, pop RDI ret is an address, but SH is, what is it?
It's an address.
Yeah, and then system is an address.
Yeah, they're all addresses. So address to that instruction, those instructions, address to that string, address to that function.
And those are located on the stack, and those are what you would write in route.
Right, so there's that RSP on the left, which is the stack pointer. So talking about the whole stack moving is us moving up the stack as we're moving things. So if that's really dim. This is a new function that says basically printf use this to call bin sh and it passes in system. So it's going to print out the address of system. We'll talk about why it's a little hard to get system in a little bit, but it's doing that and then it just pulls into a buffer, right? So when you actually do a phone challenge, it's not going to be that simple, but bear with me. So if so it's going to print out this basically. So hex 410440 would be the address to system in this case. And so if we want to actually exploit this, that looks a little bit more complicated, but in general, what we're doing is we're just snipping out the x401040, storing it into address, then we're converting that into an actual string or an actual integer, which is called system. In sh, we're storing the address to bin sh in the binary, because we have the text there, use blah blah to call bin sh. We can point to that first parenthesis, now we have a string bin sh. So that's really handy. There is actually the string bin sh in glibc, so that's really useful if you can get it. And then we're going back to that flat function again. We're going past the 16-byte buffer. We're going past RVP, and then I wish you could really see those comments because that'd be super handy. What we're doing is this first, oh, you can't see on that. There we go. This value right here is that pop RDI gadget we were talking about, and this right here is the function for system. What we're doing is we're putting sh in the RDI, and then we're jumping to system. So we're calling system bin sh, which is our goal, right? So we send that payload, and then we make it interactive mode. Yep.
So you said you got the /bin sh string from the original printf function in the left?
Right. So from the binary. Okay. So this.
Most of them are not going to have /bin sh.
So right, correct. Most programs are not going to have bin sh. I kind of made this so it would be easy for us. So we can start right here and get bin sh. But if we're going to call system, it means we have access to libc, and in libc is a hard-coded bin sh string, because the actual system function implementation uses bin sh to run your system call. So that's why it's there. But yeah, if we run this code, we will get, it'll look like this, more debug info, and then you'll see there's a little $, and I can type in ls and list the directory running commands. But there's one thing I want to ask you about that you might not know, is there's a third value in that list at the bottom there. Right, so we have the pop RDI, we have the sh that we're using to put into RDI, and we have the system call. Does anybody know what that other address is for? Anybody at all? It says ret right here. I should tell you that. This is ret. You can't see it because it's super blue. But this is an address to ret, just ret. Anyone want to take a guess why it's there? I guess Dean's going to do it. Sure.
Stack alignment.
Right. So we talked about before, like a 4-byte value has to be on a 4-byte boundary, an 8-byte value has to be an 8-byte boundary, et cetera, et cetera. What a lot of people don't know is in order to call a function, the stack needs to be 16-byte aligned for some reason. And there are normally you can get away with ignoring that rule completely, but the system function in particular will crash if your stack is not 4-byte aligned. So this ret right here basically acts as padding. So it just moves the stack 8 bytes over that address, so it's 16-byte aligned. Otherwise, it will completely crash. But we're going to talk about 2-ish more things. These are kind of the same segment. With virtual memory. As you guys have taken comp works, you're probably familiar with the idea that your program memory isn't contiguous, isn't real, isn't what it actually pretends to be, right? You have a program, you'll have your stack somewhere in memory, and you'll have libc mounted somewhere, right? You could statically compile your executable, which means libc will be included, but every program uses that, so it's kind of dumb to put it in every program. So it's when we do something called dynamic linking, where we, at runtime, your operating system will get it for you. So you don't have to carry it around yourself. But the problem is that where are all these addresses? Because we don't actually know. They could be anywhere. And that's because we have something called ASLR, which is address space layout randomization. Basically, these components are kind of random. The stack, the data segment, not really the data segment, the heap segment, libc is kind of wherever. It's a security feature, but it's also just kind of makes our lives easier sometimes. And then other than that, we also have something called position independent executable, which is called I. We like to call it I at least, which means the program can be here, or it can be completely random as well, which is even more fun. So we don't know the addresses of any of these. But we do know that they're contiguous in their own little space. They're not going to change size. So as long as we have something in there that we know its address relative to everything else, we effectively know everything. So it's really nice with the program. If we can leak something in the program, then we know where everything in the program is. Same goes for libc. So if we do, so we got to talk about these two things, which is talking about linking. Libc, right, is dynamic. We don't know where it is, but if we don't know where it is, how the heck does the program know it? It needs to call these functions. That's what these two things are for. Global offset table, GOT, and the procedure linkage table, PLT. So global offset table is kind of, I would say, self-explanatory. It's really not, but it's a table of offsets to all your functions, hence global offset table. And the PLT's job is to use that table, fill it out, read from it, whatever. So if we have our virtual memory again, and we have our program, and here's libc, whatever. Let's say we're just starting the program, we don't know where that is or anything in it. So what we have to do is our program is going to call, oh, we got these two. It's going to call something in PLT. That's what the white text on yellow says. It's going to go to the PLT. It's going to call system. So there's a little, in this case, system. We'll just say we're calling system. There's an entry in the PLT for every dynamic function you have in your entire program, every single one of them. What the PLT is going to do is it's going to read from the GOT, and it's going to do one of two things. If that entry is empty in the GOT, so it doesn't know where the function is, it's going to call the operating system, right? It's going to just go over here. It's going to say, hey, I need this function. Get this to me. And then if it gets that function, it's going to store it back in the table, and it'll be able to call the function you actually want. And then if you make that PLT call again, it will it'll have it stored in the GOT, and it'll be able to not talk to the operating system and just go into that function directly. The reason we do this instead of just populating GOTs, it would be really slow if we populated every single function every time we clicked on a program. Because users don't like that. They'll just start spamming the program and crash their computer. And then they'll complain to Microsoft, and nobody wants that. But one of the key things here is the GOT there. It stores all the functions we want. It stores the addresses of all of them. So we can leak something in there. We know where those functions are. And the other thing that's important is the PLT is procedurally updating that table, which means it's writable. There's another little exploit in here called a GOT overwrite, or I think that's what it's called, where we can actually write in our own address. And when the function wants to call, say, puts, printf, whatever, we can make it call something we want. Now, I'm not going to talk about that here because I ran out of time making these slides, but just, you could do that. Right, and so this address is effectively, the address to this function is effectively stored and got the GOT. Right, so if we wanted to do something like this with Pwn tools, and let's just say we somehow leaked, the address of gets from that function, we can load libc from the ELF. The Pwn tools will help us do that, and we can set libc's base address to be what the address of the function is in our memory minus where it is relative to libc, and that'll get us all the symbols we want without having to do any extra math, right? Because we know that maybe puts is 1,000 bytes from the start of libc. Then if we know the address of puts in our system, we know where libc starts and where every other function is, right? So where am I? I think I'm getting to the end. Yep. So we're just going to go over some tools for debugging. Adam talked about this in his Rev slides, but Jeff and Pwn tools over GDB, pretty useful. You could just use plain GDB, but I don't hate myself usually, so I wouldn't recommend that. Jeff will give you tools like patterns, where it can make a cyclic pattern. What that means is after every 8 characters, Every 8 characters of a string will be unique. So if you know you have a buffer overflow, you could paste in that pattern. And then the target value you get back, you can search for that in that pattern and get an offset. Right, so if you want to find out more about that, you can look at pattern search for Jeff, or in Pwn tools called cyclic, or just look up cyclic patterns in general. Return-oriented programming, there's 3 major tools for this. That's ROPR, not ROP. Just pretend it says ROPR. These all find ROP gadgets. Most of them are pretty similar. You only really need one of them. ROP gadget kind of sucks though, so don't use that one. I personally use RB++. And then we have, that's it. Okay, that's the end of the slides, everybody. I was also supposed to reference you to Nightmare, which is a website for Pwn. Everything about Pwn that you want to learn, Nightmare. Just Google it. I know you don't usually want to Google the words nightmare, but do it. You can also, if you want to get some intro challenges, Pico CTF has like Pico Gym, I believe it is, where they keep all their Pwn archives. We have Swamp CTF has a lot of intro Pwn and buying exploitation. So if you want to go to the 2024 archive, it's just 2024.swampctf.com. You want to get intro stuff there, and then Hackbox also has a bunch of challenges. So I apologize for not having the most put together presentation, but I think it looked great.